Thank you for introduction, Mr. Chairman. Good very afternoon, ladies and gentlemen. My presentation will be divided into 4 parts. Short introduction, after that I will describe our material and experimental background, and then I will result, and after that I will conclude my talk. You probably know superalloys are materials known already for decades, which are used for high temperature applications like turbochargers or turbine blades. This material is still interesting for material science. They are, for example, undergoing changes of cyclic plastic deformation mechanisms with increasing temperatures. And one of the open questions in these mechanisms is original and mechanism of crystallographic stage cracking, which is observed in temperatures around 600 to 800 centigrades, which is still not well understood and just rather experimentally analyzed. And this is the area on which we focused in this study. Our alloy was RM247 superalloy, which is cast polycrystalline one with this chemical composition. The material was at first processed by hot isostatic pressing at these conditions, and after that follows 2-step heat treatment consisting of solution annealing and precipitation annealing. And we obtained coarse dendritic structure with average grain size around 0.8 millimeters, and also in structure we found some shrinking pores in size up to 0.4 millimeters. This material is characteristic for strengthening phase gamma prime. In our case, we had approximately 60% of volume fraction. We had 2 types of precipitates in the material, cuboidal one with edge size about 400 nanometers, and spherical one with diameter of 2 micrometers. And also we had in the microstructure numerous carbides along the grain boundaries, and carbides of MC type in interdendritic areas. All fatigue tests were done on resonant testing machine hamster in a load control regime with Fourier reverse loading. Test frequency was 120 Hertz, and we had 4 test temperatures: 650, 800, 900, and 950 centigrades. Here come first results. Fractographic analysis. I put here examples of fracture surface from each temperature, where you can see distinct changes of appearance of fracture surface. When a temperature is 650, you can see almost brittle-like fracture appearance, which is at stage 1, correct propagation. Here on all pictures are initiation sites highlighted by black arrows, and you can see that with increasing temperature, this mode of grain propagation is changing. At temperature 800 centigrades, it's already just in some areas in vicinity of initiation sites, and from temperature 900 centigrades and upper, we didn't observe this mode already, and the oxidation was gaining the importance in damage mechanisms. So as I said, we had at temperature 650 extensive crystallographic grain propagation across almost the most of the fracture surface, and with increasing temperature, this mode was disappearing. Here already some curves from our fatigue tests. You can see 4 curves representing each temperature, and from this diagram it's obvious that one curve, and it is curve representing tested 650 centigrades at different slope than other 3, and this is this is another evidence that in this matter is going some change of mechanism, of damage mechanism, where at this temperature we observed that stage 1 crack mode, dominant stage 1 crack mode. Other three temperatures had already similar slope of these curves, and we observed just slight decrease of fatigue properties with increasing temperature. The best fatigue performance was measured at temperature 800 centigrades, which is also highlighted by highest fatigue limit. The significant scatter of experimental data is given by cast nature of material with coarse structure. After this study, after these measurements of fatigue tests and plotting of these curves, we focused on explanation of this different slope. We prepared axial sections along the loading axis by polishing and etching to prepare samples for substantial electron microscopy observations, and one of the first observation or analysis was EBSD analysis. Here I put two specimens to show the example of different mechanism. Here is one axial section from specimen from fatigue test at 650 centigrades. Here is from 900 centigrades. Fatigue crack initiated in both cases in grain number 1. In this case, the grain were almost identically oriented with planes with same Schmidt factor, almost same Schmidt factor, and you can see that behavior of the crack was quite different at both temperature. So therefore, there is really some different mechanism going on. In this case, we were also able to ensure that crack is really propagating along slip planes of type 111. So this type, as you will see further, is really crystallographic dependent, this stage 1 mode. So here are some examples of fine observation of this axial section, where we were able to find evidence of localization of cycloplastic deformation along the slip planes of type 111, which are visible here in this detail from this area. And you can see activated slip planes with nice shearing of precipitates. Here are other examples, here in front of the crack tip, and here in one of the large grain, inside of this grain, severe plastic deformation going along slip plane in numerous places. We made some procedure, like first fractographic analysis, choosing of cross-section plane, which is interesting for us. EBSD analysis was the second step, and as you can see, I chose this area, this small grain, which was where I found the localization. I hope it's at least a little bit visible. It's highlighted by yellow arrows, this line. And we prepared some flip cut by focus ion beam and scanning microscopy. And in another slide, you will see that in this area, it wasn't just some shearing of precipitates, but we were lucky and found already developed stage 1 crack. And here is image from scanning mode of transmission electron microscopy, where is visible the crack, which is going along the plane 111, and this plane is with very high Schmidt factor. Here you can also see planar character of dislocation structure. With closer look on this transmission electron foil, it was visible that there is more slip planes activated, not just the one. This is the slip plane of crack, but we have additional one, the slip plane 101, and also 111-1, where the dislocation density was quite significant. At this temperature, 650, where we observed the crystallographic crack mode mostly, we can say that dislocation structure is mainly planar, crystallographically dependent, and in some grains, or maybe in most of the grains, are numerous slip planes activated, and the crack follows just one of them. Temperature is 800 centigrades. I chose another specimen and we did the same procedure. Again, EBSD analysis in this area. I found the localization of plastic deformation. Here are visible slip shearing of precipitates. And this is the area of FIB cut where I extracted the transmission electron microscopy foil. And here is image of the foil, and you can see nice planes with shearing of precipitates with significant dislocation density. And again, this shearing is on slip plane with very high Schmidt factor. Here is another image of this area where I can conclude that planar alignment of dislocation is already not so pronounced like at previous temperature. So we had, in this case, we had just one slip activated, but there is already more dislocations in channels of gamma and also in interfaces of gamma prime. We made some other observations by electron channeling imaging, where it's also possible to see some evidence of cycloplastic localization. I'm showing these pictures because of crack tip, where it is visible that the plastic deformation is concentrated, let's say localized, just into this slip plane in front of the crack tip, and that crack tip is discontinuous. That on this slip plane are probably creating some voids, which and crack is growing by coalescence of these voids. Here are some pictures from conventionally prepared foils, where again they are showing planar character of dislocation structure at the temperature 650 centigrades, which goes well with the fractographic analysis what I showed at the beginning. This planar character is disappearing with increasing temperature. Here it was already not so pronounced. We had already dislocations in the structure of material in channels and interfaces of precipitates. And at the highest temperature, 950 centigrades, we had already almost homogeneous dislocation structure, which tend to show us that dislocations were already well mobile, so they were able to avoid the precipitates and were not restricted just to slip planes. Therefore, we observe typical stage 2 fractured surface with fish eyes and striations like at normal metallic materials. Let me conclude my talk. I show you that at temperatures 650 centigrades, was observed planar dislocation structure, shearing of fine precipitates on multiple slip systems, and most of these locations were blocked by coarse precipitates. And therefore, we observed crystallographic cracking, stage 1 cracking, which was represented on majority fracture surface. At 800 centigrades, shearing of fine precipitates was also observed, but in smaller extent and on less slip systems. Therefore, crystallographic cracking took place just in the vicinity of crack initiation sites, and further crack propagation was in stage 2 mode. At temperature 950 centigrades, dislocation structure is quite homogeneous. Dislocations are able to avoid coarse precipitates already because of high dislocation mobility, and therefore we observe classic stage 2 fatigue propagation. Thank you for the attention.